So in my previous class, I will uh, I have talked about the second order linear differential equation and its different form, and how do I get the general solution of different types of differential equation when the form of coefficients are known. So any general linear differential equation which is a second order equation that can be written as P0 x y double prime plus P1 x y prime plus P2 x y, this equals to f of x. Okay, now for our sake of simplicity, I will assume that this f of x is 0 here. Now the form is reduced as P0 x y double prime plus P1 x y prime plus P2 x y, this equals to 0. Okay, now as if you remember my first class, you will see that this differential equation can be simplified by dividing the whole thing by this P0x. So what I will get, y double prime plus P1x P0x into y prime plus P2x P0x y, this will be 0, right? Now if you say that this P1x by P0x as Rx and P2x by P0x as Qx, so this differential equation reduced as y double prime plus Rx y prime plus Qx y, this equals to 0. Now solution of this differential equation depends on form of this Rx and Qx. Okay, so if Rx and Qx are constant, then we can use the normal second order rules that the power mx is a trial solution and you will get different roots of m, and from that you will just generate two general solution. But if Rx and Qx are the function of x, then this method is not working, not a trial solution as e to the power mx. Okay, so this, for this method, when px and rx and qx are the function of x, then you have to apply series solution, and in this series solution you have taken y as a power series x to the power n, and then you put this power series, this equation trial solution, in this differential equation, and you will get some recursion relation. From that you will find out the different coefficient an. From that you will get the general solution. Now this is a method when provided this Rx and Qx, they are analytic at x equal to 0 here. Now choose a point x equal to x0 by inspecting this differential equation. Okay, so looking at this differential equation, you choose such a point x equal to x0 where this Rx and Qx, they are not analytic. If they are not analytic at x equal to x0, then this x equal to x0 is called a singular point, right? So if x equal to x0 is a singular point, then what should we do for getting the solution? So my first work is see whether this Rx and Qx, they are singular at this point, but see whether this x minus x0 Rx and x minus x0 square Qx, they are analytic or not. So when you find this solution by inspecting this equation, so how can we inspect this equation? Say for example, this Rx has a form of 2x divided by x minus 1, right? And this Qx has a form x square divided by x minus 1. So from this first equation, you will see that the form of this P0 is basically x minus 1, right? And it will divide x minus 1 in here. So P1x is 2x, P2x is x squared. So if this differential equation looks like this, and what you will get that this x equal to, at x equal to 1, both Rx and Qx are non-analytic. So at x equal to x1, this point is singular point, right? Now by inspecting this equation, you will find that x equal to x0 is a singular point, but x minus x0 Rx and x minus x0 square Qx, this is analytic. Okay. So if the situation appears like this, and you will find that these two forms are analytic, then according to Frobenius, general solution or the trial solution can be taken as y equal to x minus x0 to the power m sum over n equal to 0 to infinity a n x minus x0 to the power n, right? So now remember the series solution, what you will get in series solution, if x equal to x0 is a ordinary point, then there will be no hesitation of choosing y equal to a n x to the power n as a solution, because this is the power series. Okay, and I have told in the first class that use of power series has different types of facility. So we are add them, we are subtract them, we are differentiate term by term. So these are the benefits. Okay, now if there is a singular point, you have to use an extra term x minus x0 to the power m along with this power series. Now what is the significance of this term? Now if someone is going to appear in some interview board, then what he will do? He will just get a good get up and he tries to show the best performance, right, in the interview board. Now the same thing happens in here, because when you are taking x minus x0 to the power n as an extra term with this series, okay, more number of solution you can accommodate in this series. Okay, so for regular singular, so you can use more number of terms, more number of solution, a general solution in this series. Okay, now this point when x minus x0 q square qx and x minus x0 rx, they are analytic, then x equal to x0 is called regular singular point or removable singular point, or these are called non-essential singularity, right? So if you use this trial solution for getting the solution of this particular differential equation here, and this point is regular singular point, you can use this Frobenius method to get a solution. Now why this term is important? Let us consider you are using a general series where you will get a solution like this, root x. Okay, so x to the power half might be a solution of any differential equation, though there exists a regular singularity, right? Now if you differentiate this term, what you will get? You will get 2 root over x. So at x equal to 0, this 2 root over x is non-analytic. But when you introduce this term, you can cope up all types of solution in this differential equation or in this solution. So your appearance of solution becomes much better than that of using a simple power series, right? So this is the significance of this term. Now what you will do here, you will have to solve this equation. So how could you solve this equation? So for non-essential singularities or the regular singularities, this method is basically applicable. Now if this method is applicable at x equal to x0 as a regular singular point, now there always exists a series solution like this form. So the general solution of this equation will be a n x minus x0 to the power m plus n, right? With provided with using a0 not equal to 0. So this is basically the choice of Frobenius, which is choosing for solving this regular differential equation having this regular singular point. Now we have to determine m, but how? Let us consider this solution. Okay, and obviously this solution must satisfy this differential equation. Okay, so you have to put this solution in this differential equation and you will get a second order equation of m, okay, with coefficient of n equal to zero index term of x. So at the time of determination of m, you are choosing n equal to 0. So what you will get from this differential equation, you will get a form like this, a0 fm. And for Frobenius method, I am choosing a0 not equal to 0. So there will be no problem that if this is 0, then fm will be 0. This is nothing but a quadratic equation of m, as there exists a second order term. So by solving this quadratic equation, you can get different values of m. Now, depending on the values of this m, whether they are equal or not, this solution becomes different, right? Now, this quadratic equation is called indicial equation. Okay. From this indicial equation, you have to choose a term of x, and you will get the solution by applying this power series. And when you put this power series and the special for values of this m, which you will get from this indicial equation, then you will get some relation among the different terms of am in terms of either a0 or a1. So that relation is called recursion relation. So after using this recursion relation, which we will use in case of normal ordinary points series solution, now from this recursion relation you will get different terms a0, a1, a2, a3, different terms, and you will get the solution. Now how can you find this a0, a1, a2, this term? I will come to this later, but before that I will tell something about the form of solutions. Now, if the roots depends on the solution of indicial equation. Okay, first case, say for example the roots of indicial equation, they are distinct and they do not differ by integer. So the roots are distinct and they are not differ by this integer. Then the complete solution y equal to a y bar at m equal to m1 plus b y bar at m equal to m2, where this y bar is the trial solution which you will get using just the recursion relation. Okay, now second case, when roots are equal. When the roots are equal, then complete solution has the form y equal to a y bar, that is the trial solution at m equal to m1 plus b d del y bar by del m at m equal to m2. Okay, so for m equal to m2, you will get this differential equation and you will get the solution. Now there are third cases. Which is the third case? Basically, the roots are distinct and they are differ by integer. Okay, in that case, y will be a y bar at m equal to m1 and b del y bar by del m at m equal to m2. But the problem is that when initial root gives us distinct root and they are differ by integer, and among the two roots m1 is less than m2. Okay, for case 3 this m1 is less than m2, then the greater root of the two, that means m2, that will yield solution, while the smaller root m2 that may or may not yield solutions, right? So in the later case, when this equation may not provide any, may not yield any solution, then we have to choose a special form, or we have to set the form a0 equal to b0 m2 minus m1. So we have to set this term by this to get the solution. So I am repeating the same thing again. You will choose the initial equation here, and in this initial equation you will get two distinct root of m, that is m1 and m2, as this is, that is a quadratic equation. If m1 m2 are two roots of these initial equation, and these two roots are basically distinct and they do not differ by any integer. So m2 minus m1 or m1 minus m2, they are not integer. Then the complete solution can be written as a y m at m1 m equal to m1 and b y bar at m equal to m2. But if the roots are equal, if the roots are same, then complete solution is a y bar at m equal to m1 plus b del y by del m at m equal to m2. But another thing is that if the roots are distinct and they are differ by some integer, so you will get the solution in this term. And if for case 3 m1 less than m2, then m2 yields a solution, m1 yields the solution, m2 leads the solution, but m1 not. m1 is less than m2, so m1 may or may not yield the solution. So if m1 may or may not yield the solution, if it may yield the solution, then there is no problem. But if this m1 may not yield the solution, then we have to choose a special form of a special relation between a0 and b0, that is a0 equal to b0 times m2 minus m1. So in this way you will get the solution. Now I will show you how could we use this power series to get the solution. So an example here: solve this power series, solve the differential equation 2x square y double prime minus x y prime plus x square plus 1y, this equals to 0. So this is basically the differential equation. Now if you divide the whole term, what you will get? Y double prime plus 1 by 2x y prime plus x square plus 1 by 2x square y equal to 0. So this is basically Rx and this is basically Qx. So what we will get? That Rx equal to 1 upon 2x and Qx is x square plus 1 by 2x square. Now if you put at x equal to 0, what you will see here, that at x equal to 0, Rx is 1 by 0, so undefined, and Qx is 0 square plus 1 by 2 into 0 square. So this is also 1 by 0. This is undefined. So x equal to 0, this is a singular point for this differential equation. But limit x tends to 0, x into Rx, what is the form of this? So limit x tends to 0, this will be x 1 upon 2x, so this will be half, and limit x tends to 0, x square qx, so limit x tends to 0, x square into x square plus 1 by 2x square, so this will be 1 up by 2, right? So in both the cases you will get a number, a real number. So these two terms are analytic, right? So x into Rx and x square into Qx, they are analytic at x equal to 0 point. So this x equal to 0 point is a regular singular point. Okay, so as this is a regular singular point, you can use the Frobenius method for solving this differential equation. So let us choose the trial solution as y equal to sum over n equal to 0 to infinity a n x to the power m plus n. Okay, and when you choosing this as the trial solution, y prime will be m plus n within the sum n equal to 0 to infinity a n x to the power m plus n minus 1, and y double prime, this will be m plus n minus 1 n x to the power m minus 2, right? Now the form of that differential equation, which you will get 2x square y double prime minus x y prime plus x square plus 1 by 2x into y equal to 0. So in this case, sorry, I am writing a wrong term. This will be minus, so this will be minus again, this will be minus half, yet this is analytic. Okay, so this is basically x square plus 1 into y, this will be 0. Okay, so this is the differential equation. Now you have to put the form of y double prime here and y prime here. So what you will get? You will get general solution as sum over n equal to 0 to infinity 2 times n plus m into n plus m minus 1 a n x to the power m plus n, because this is m plus n minus 2. If you multiply x square with m plus n minus 2, it will again gives me x to the power m plus n minus sum over n equal to 0 to infinity. Now for the second term, here is x, so again x to the power m plus n minus 1 into x, this will be x to the power m plus 1, so this will be m plus n into a n x to the power m plus n plus, I will divide these two terms. One is x square y and another is only y. So for x square y, the term will be a n x to the power m plus n plus 2, and for 1 this will be a n x to the power m plus n. So this will be 0, right? Now if this is so, and of course you will choosing the condition that a0 not equal to 0 here, right? Now equating the coefficient of x to the power m plus n, because this is the minimum coefficient of x to the power m plus n. So equating this coefficient m plus n equals to 0, when n equals to 0, this is the minimum coefficient of x. So minimum index of x will be x to the power m here. So equating the coefficient of x to the power m equals to 0, you will get the recurrence relation, where this recurrence relation gives me just 2 into m into m minus 1 a0 minus m a0 plus, this will be 0 because this is x to the power m plus 2 coefficient, so I will have to leave this, and what you will get so this will be m plus n, so m sorry, this will be m a0 plus, this will be just a0, this will be 0. So from this equation what we will get, you will get 2m m minus 1 a0 minus m minus 1 a0, this is equal to 0. So 2m minus 1 into m minus 1 a0 equal to 0. So this is basically the initial equation. So as you see here, this is the initial equation. From this initial equation, you have to find two roots of this m. One root is m equal to half and another root is m equal to 1. So these two roots, they are distinct, but they are not differ by integer, right? Okay, now equating, now you will have to find recursion relation. So equating coefficients of x to the power m plus 1 equals to 0, what we'll get? We will get different terms of a2, a3, etc. And from this equation, what we will get? We will get just two into m plus n into m plus n minus 1. This will be an minus m plus n times an plus, as this is x to the power m plus n plus 2. So as you see in my first class, that you have to reduce this coefficient by 2. So this am will be reduced by an minus 2. So this will be just plus a n minus 2 plus an, this will be 0. Now you have to just simplify the whole term here. So what you will get? You will get that this will be m plus n into m plus n. I will just m plus n into 2m plus 2n minus 2n minus, you just take this term inside. So what you will get? You will get the m plus n minus 1 times an plus an minus 2 plus 2 0. Now you are just taking take this m plus n minus 1 here. So what you will get? 2m plus 2n minus 1 into n plus a n minus 2 is equals to 0. Now the same thing you can use just in another form, that if you take m plus n common from this equation, what you will get? M plus n into 2m plus n, 2m minus 2, okay, minus 1 plus 1 a n plus a n minus 2 plus 2 0. Okay, so both are correct. So this is also correct, this is another form, this is also correct. Okay, now from this equation what we will get? We will get the value of this different an in terms of an minus 1. So as you look here, this series starts with n greater than equal to 2. But before that, if you choose n equal to 0 or n equal to 1, this will be in a minus 2 and a minus 1, which is absurd. So I have to use this term n equal to n greater than equal to 2 here. So what you will get? You will get the recursion relation as a n equal to 1 divided by m plus n into 2m plus 2n minus 3 plus 1 into n for n greater than equal to 2, right? And from initial equation, you will get two different root at m equal to 1 and m2 equal to half. Okay, so these two root you will get from initial equation. Now what we will take, just look at the initial equation here. So initial equation will be m minus 1 into 2m minus 1 a0 x to the power m equal to 0, and your preferable choice that a0 is not equal to 0. So if a0 is not equal to 0, m1 will have m1 and m2 two roots. Now same thing happened for the second term. So if you choose n equal to 1, what you will get? You will get, by applying n equal to 1 here in this equation, if you choose n equal to 1, so what you will get, in 2 into m plus 1 m n, so m into m plus 1, here you will get just m plus 1, here you will not, this term will not give any term, and 1. Okay, so the term will be just, I am looking at this white portion. So for n equal to 1, that is 2 m plus 1 into m a1 minus, for n equal to 1, so this will be m plus 1 a1, and this term will not give me anything, and this will be just plus a1. So what we will get from this, we will get just m plus, so this will be m plus 1 into 2m so m plus 1, this is 2m minus 1 plus m into a1, this will be 0. Okay, so as you choose m equal to, just here m equal to what you will choose, your preferable choice, that m equal to either half or 1. Now you, if you put m equal to half or 1, this term will not become 0. So if you put m equal to 1, what is the value of this m equal to 1? This will be 2, this will be 2 minus 1, that is 1 plus 1. So 2 plus 1, 3, 3a1 equal to 0. And m equal to half, this will be half, so this becomes 0, 1 into a0. So my proper preferable choice is a1 equal to 0 to make this initial equation survive. Okay, so by inspecting the term, you will have that for n equal to 1, that is a1 equal to 0. This is my choice to survive m equal to half, m equal to 1 value. Okay, now once you get this equation, so this is basically my choice. So when you choosing this term from recursion relation, you will automatically get that a1, a3, a5, because an is related to an minus 2, right? So n equal to 3 means 3 and a1, n equal to 5 means 5 and 3, n equal to 7 means 5 and 7, so a7. So as a1 equal to 0, Then a3 equal to 0, a5 equal to 0, similarly a7 equal to 0. So all these terms become 0 if I choose a1 equal to 0 here to survive this initial values. Now we have to find out the values of different form of recurrence relation. So recursion relation is an equal to 1 divided by m plus n into 2n plus 2n minus 3 plus 1 into an. Okay, and this is n greater than equal to 2 here. So now as n greater than equal to 2, so sorry, this is n minus 2 here. So if you put n equal to 2, what you will get? So a2 equal to 1 divided by m plus 2, and from here this will be 2m into 2 times 2, so 4 minus 3, so this will be 2m plus 1 plus 1, right, for n equal to 2. So for n equal to 4, what is the value of n equal to 4? This will be a4, so this is into a0. So n equal to 4, so a4, the value of a4 is basically 1 divided by m plus 4 into, so 4, 2 times 4, this becomes 8, so 8 minus 3, this will be 5, so 2m plus 5 plus 1 a2. Now we have to put the values of a2 here, so what you will get, 1 divided by m plus 4 into 2m plus times 1 times m plus 2 into 2m plus 1 plus 1 a0, right? So you will choose two term. One is n equal to 2, n equal to 4, right? Now complete solution is written as y bar, so this will be a0 in terms of a0 plus a2 x square plus a4 x to the power 4 plus dot dot dot, as a1 equal to a3 equal to a5 equal to a7, these are all 0. So the solution will be 4, but a common term is here x to the power n. So solution becomes a0 x to the power m times, first term will be 1, and the second term there will be sorry for, but here exists a negative sign. If you calculate this, you will get a negative sign here, so a2 will be negative, a4 will be positive. Okay, so sorry for this negative, so here will be a negative sign, so 1 minus this will have x square divided by m plus 2 into 2m plus 1 plus 1 plus 1 divided by within third bracket m plus 2 2m plus 1 m plus 4 2m plus 5 plus 1 into m plus 2 into 2m plus 1 plus 1 into x to the power 4 plus dot dot dot. So this is the solution of y prime. Now when m equal to half and special choose a0 equal to 1. Okay, so what you will get? You will get y1 as this is a0 equal to 1 and m equal to half, so this will be root x. So root over x 1 minus x square by 6 plus x to the power 4 by 168 minus, if you put the values of this m equal to half, you will get the solution. And similarly, when m equal to 1 and a0 equal to 1, you will get y2 as x 1 minus x square by 10 plus x to the power 4 by 360 minus dot 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 dot. Now you see here, this root x is one of the solution. Okay, now if you use any ordinary differential equation, ordinary just power series, then this root x, you cannot differentiate this root x at x equal to 0, because if you differentiate y1 as a root and if you put in that particular differential equation, you will see that the value of this root x will be 1 by root 2 as this is here, and this function, this solution becomes non-analytic. But using this Frobenius method, you can introduce the fractional value of this roots, that is root over x, 3/4 x, root x. So all types of solution you can put in the same form of solution. So this method is far better. Okay, now the complete solution will be as you see here. So here the roots are basically different, but they are not distinct by any integer. So complete solution will be a y equal to a y bar plus y1 bar b y2 bar. Okay, so this is y1 bar, this is y2 bar. So I have to write the complete solution as y equal to a root over x into 1 minus x square by 6 plus x to the power 4 by 168 minus plus bx 1 minus x square by 10 plus x to the power 4 by 360 dot dot dot. So these are the complete solution. Now just a gist of this total class which I am taking. So if you have any differential equation of this term, you have to just divide the whole differential equation by this coefficient P0x to get the differential equation of this form, that is y prime r x y prime y double prime r x y prime q x y equal to 0. But here the solution depends on this rx and qx obviously. And if you see here, for a ordinary point, if this x equal to x0 is the ordinary point, then you can have the solution in this form: y equal to sum over n equal to 0 to infinity a n x to the power n x, and if x equal to x0 is a point of solution, so you are going to find out the solution in the neighborhood of x0 point, then you will take this as a an x minus x0 to the power n as a power series. But the problem is that if x equal to x0 is not a regular point or a ordinary point, but there at that point Rx and Qx both are non-negative, then this x equal to x0 called a singular point, and around that singular point you will have to find the roots. Now you can able to find the root if this function has got a regular singularity at x equal to x0. But if there exists no regular singularity, only just an ordinary singular point, then you cannot find any differential solution of the differential equation at that point. So for getting the differential equation, getting the solution, this x equal to x0 point need to be a regular singular point. And how can you expect that x equal to x0 whether this is regular singular point or not? You have to use this function x equal to x0 rx and x minus x0 square qx. If these two terms are analytic, so limit x tends to x0, this and x tends to x0, this, they are analytic, then you can say that yes, I am able to get the solution of this differential equation. Now, according to Frobenius, the trial solution will be x minus x0 to the power n sum over n equal to 0 to infinity a n x minus x0 to the power n, provided a0 not equal to 0. Okay, so the complete solution, the trial solution will be y equal to a n x minus x0 to the power m plus n with the special choice of coefficient, that is a0 not equal to 0. Once you use this a0 not equal to 0, you can able to find the initial equation of this differential equation. Now, what is the initial equation? Initial equation is that from which you can determine the values of this m. As this is the second order differential equation, so this m has got a quadratic form if you choose n equal to 0 in this solution. Okay, and choosing n equal to 0, you just put this solution in this particular differential equation, and when you put this solution, you will get a just an quadratic equation of m, where a0 you choosing a0 not equal to 0, so in this case fm will be 0. Now fm will be 0, fm equal to 0, this is an initial equation. From this initial equation you have to find out the roots of m, and when you find out the roots of m, depending on these roots you will get the different form. And as you see here, there will be some relation between different coefficients of this differential equation, and those relation is called the recursion relation. From recursion relation you will find the values of a0, a1, a2, a3, etc. once you get the values of m and m1. Now there will be a special form, and the roots depend on the solution of this initial equation. Now if the solution of this initial equation m1, m2, they are
basically distinct, but they do not differ by an integer. Okay, then the complete solution is y equal to a y bar plus b y bar at m equal to m1, at m equal to m0, m2. And if roots are equal, then the complete solution is a y1 at m equal to m1 plus b del y by del m at m equal to m2. Now, if the roots are distinct and they differ by some integer, then the equation will be same, but here exists a problem when m1 less than m2. If m1 less than m2, and then the greater root gives us some solution, because here m2 is greater, so m2 must yield some solution, but m1 may or may not. When M1 may yield some solution, then there will be no problem. But when M1 may not yield the solution, then you have to choose this A0, this B0 as a special form of A0, and the relation between A0 and B0 will be A0 equal to B0, M2 minus M1. So this is the complete course of applying just Frobenius method. And what is Frobenius method? I'm just giving an example here. When the roots are equal, now it is your homework. When the roots are non-equal, you have to find out the solution. So thank you for your attention.